Hello and
Hi.
welcome to Engineering with Rosie Live. Hi to our guest today, Dr. Linda Stalker.
Hello.
I will get to Linda's proper introduction in a second, but first up, let's just thank the sponsor of these live streams, which is WeatherGuard Lightning Tech. WeatherGuard make Strike Tape, a retrofittable lightning protection system for things that go fast, like wind turbine blades and aeroplanes. I just want to start by asking a viewer question. So, as always, keen to know where you're calling in from. Bit of a weird time today because we're working across both sides of Australia with me in Canberra and Linda in Perth. Where are you calling in from? And yeah, about today's video is going to be on carbon dioxide transport and storage. So my question is, do you think that you understand how CO2 storage works? And then if yes, do you think it's a mature technology, or what aspects do you think need to be developed further before it could play a real role in lowering CO2 levels? So yeah, I just might start before we get into the thick of it, start with why I wanted to do this video. So it's like a couple of years ago now, I started researching carbon capture and storage just because I wanted to look into blue hydrogen. So hydrogen made from methane and then with the carbon dioxide stored. And I couldn't find any information about carbon capture to really be able to form an opinion. So that led to the first video I did on this topic with chemical engineer Mark Allen, about how the capture part of carbon capture and storage works. And yeah, there is a video on the channel. I think I put the link in the description if you want to find that. And yeah, I was a bit surprised to learn that the technology really is mature, it works, and other industries are doing it, no worries. Yeah, it is obviously also expensive, and when we don't put any value on CO2 going into the atmosphere, there's just no real reason for anyone to do CCS. So anyway, the next step is obviously to look into the transport and storage part of CCS. So that's what we're going to talk about today. My hope for this live stream is to talk about the technical aspects. I found it's really hard to find information about how these things actually work. There's just so much emotion and passion on the topic, which is great, but I think it's really good to understand how something works before you form your opinion about whether you should or shouldn't do it. So I'm hoping that this video can be part of that. Yeah, and I just wanted to continue with a question that I had from the Engineering with Rosie with the Engineering with Rosie Patreon team. John asked, so we've got companies claiming that the future is in CO2 storage, and they have close to unlimited cash right now and the best drilling capabilities and technology in history right now. So why isn't it already solved? And I think that's a really good question that I'm going to ask Linda to hopefully help us to understand what's going on. So yeah, that's all of my little introduction out of the way. So Linda, could you please introduce yourself in more depth? Why have you gotten to this point in your career, your history working with CCS and your education, all that sort of thing?
Okay. Well, thanks for having me today. And you'll hear already there's a bit of an accent going on. So I've did my undergraduate degree back in Scotland a long time ago in applied geology at the University of Strathclyde, and then went a tiny bit south to Newcastle upon Tyne. And I did a PhD looking at the origin and fate of carbon dioxide in North Sea oil fields. And that was published in 1994. So I've been doing this for a wee while now. I've bounced around doing postdocs and things like that, and I guess one of the interesting things I did before my latest position was I spent about 4 years working in Norway for the company then called Statoil, now called Equinor. And in Norway, there is a vibrant carbon capture and storage as well as oil and gas industry there. And I was working in exploration and production there for a couple of years, including the Sleipner field. And if you do have some knowledge about carbon capture and storage, people are familiar with the fact that the Sleipner field has been injecting CO2 there for quite some time. Now, I was working in the oil and gas part of things, so it wasn't actually till I came to Australia that I found out that they were actually taking the CO2 that was naturally occurring in the hydrocarbon field and storing it underground elsewhere offshore. So that was 1996 they commenced injection there, and they're still doing it today. In 2000, I came to the CSIRO, so that is, for those not in Australia, the sort of federal government sort of the Australian Science Agency, where we do research that addresses challenges for Australia. And I've been here 23 years and working on sort of subsurface geoscience, including carbon capture and storage for most of that time.
All right, interesting background, and I am a bit jealous that you got to live in Norway for a while. That was my favorite place to go when I lived in Europe. I think, yeah, like my top 3 holidays that I did while I lived there were all to Norway, so that's nice. Okay, so let's just have a look at some of the viewer questions. We've got people calling in. Lois Lane is calling in from Germany. Mark Nicholson from Melbourne. Mark Klein from Canada. Yeah, all over. So I'm always surprised when we do these at the times of day that people are up watching YouTube videos. But thanks everybody for tuning in, no matter what time of day or night it is where you are. I also like this comment. I always like to watch your presentations. They're really engineering stuff. And yeah, I think that's might not sound like a compliment to many people, but I do appreciate that. That you appreciate, the geeky technical stuff. So with that in mind, let's move on to the meat of the topic. So I wanted to start off with what is carbon capture and storage. We maybe actually I might start by sharing a poll that I did on YouTube ages ago, because we have rescheduled this one a few times. I'll just share that now. Where is it? So I asked, what's the biggest hurdle for CO2 storage being able to make a real contribution to solving climate change? And 52% of people said the economics don't add up. And then, next most common is pretty even technical challenge, doesn't work and never will. Technical challenge that needs more development, and then lack of funding and investment. So I don't know, what do you think about that, Linda? Just like broadly, obviously we'll go into all of these issues in more depth, but does it surprise you that that's what people thought?
From the perspective that I think they're bang on the money, to pardon the pun, the economics are a big challenge currently, and market signals will really help, as well as other investments. So yeah, absolutely. And the flip side, that only 4% are concerned about environmental risk, because it's actually a pretty safe technology to use. So you've got a really informed audience. I'm quite impressed.
No, I was surprised too, a little bit, at the response, but it's good to be surprised. That's what keeps it interesting. Okay, so I did have one other question from the Patreon group from Jeffrey, who asked, can it scale enough to have an impact? And I think that that's a really good segue into, this is why I think that, CCS is worth even talking about. It's because it's one of few technologies, negative emissions technologies, or ways to actually get carbon dioxide out of the air that actually has the possibility to scale. So I just want to move on now to one of the slides that you presented, and maybe Linda, we can start by talking about what are the different ways that you can capture capture carbon dioxide, and with scale in mind when you're talking about them.
Mm-hmm. So there's kind of like 2 key areas that people look at. There's sort of like capturing point emission sources, or there are direct air capture technologies. The point emission sources are things that people do tend to sort of like relate to the oil and gas sector, because they developed a lot of that early technology using amines to strip the CO2 out of natural gas streams that had high CO2 contamination. And the driver initially there was that you can't keep the CO2 in with your natural gas, because it doesn't burn, it has no calorific value. Also, in the presence of moisture, you start to develop carbonic acid, and then that starts to destroy your infrastructure. So there was always a driver to take that CO2 out of oil and gas. So amines have been pretty typically used on and offshore. People have also looked at membrane methodologies and cryogenics, but they're really about large-scale point emission sources to do that. In more recent times, they've been doing more work in direct air capture, and these involve sort of almost like banks of standalone units that will try and take the CO2 out of the atmosphere, because this is where it's where we get to the pointy end of things. It's the impact on the atmosphere about in relation to high CO2. So there are a lot of people looking at, can you use liquids like amines? Can you use solids, sort of absorbents, molecular sieves, or can you actually like smash them together and do that as well? So those are the two really large-scale activities, but acknowledging that there are other methods like soil carbon, mineral carbonation, utilization, and making new products, but they're not at the same scale. And that's why carbon capture and storage is present in the sort of portfolio of tools to use for reducing those emissions.
Yeah, okay. And those technologies I have covered on a few other videos, and will continue to in the future. But I think there was one video I made on carbon uses, and one of the lines that I said in that I like to repeat is, you can turn carbon into alcohol or diamonds, but there's a reason why we measure diamonds in carats and not in billions of tons, which is kind of the scale that we need. We've got a really good viewer question now that might lead us into another point on scale from Fred Blogs. If the world transitions to renewable electricity, then carbon capture becomes irrelevant because over time it'll solve itself. If we don't, then the energy required generates more than is captured. So there's a bit in there, but I think I might rephrase that a little bit into why would we need carbon capture, which is quite a tricky technology when we're going pretty well on renewables. Is there, even if we have 100% renewable electricity, is there still a place for carbon capture once we've done all of that?
Well, there's a lot of industrial processes that actually emit CO2 as part of that product. So cement is one of the big ones. It is a huge contribution to carbon dioxide generation, and it's not because it's using high amounts of energy, which it is as well. So you can't renew your way out of absolutely all of these activities, and so but your Fred's right on about the fact that over time this transition will take place, and there will be less need for things to do with CCS in terms of like the fossil fuel sector or the energy generation sector as renewables come into play. But it doesn't necessarily mean that people won't use hydrocarbons for products down the track rather than just combusting them. So I think there is an expectation that will change over time, and the quantum will change over time, because the clue is in the words energy transition. So I think that's really important to remember, that over time, the interplay of all these different technologies that we will require to use will be important, and the economics also really become challenging as well. To renew absolutely everything becomes sort of like exponentially more expensive over time. But if you have a toolkit of different things all contributing, you can start to deal with the costs a bit more effectively.
I'd probably add that you mentioned cement, which is one hard to decarbonize area, but there's a few sources of emissions that aren't related to energy or electricity. Agriculture is another one.
Agriculture. It's really hard to abate some of the vehicle stuff at the moment until that whole switch takes place. And if we do all move to electric cars, the amount of additional electricity that needs to be generated is frankly eye-watering. So there's a lot of really big numbers at play in this, and it really makes it challenging. So if carbon capture and storage can deal with some of that, that's hugely beneficial to all of the other sectors that we're actually trying to bring on as well.
Yeah. Okay, so let's move on now to the technical aspect of carbon dioxide transport and storage. Can you tell me or tell us, Linda, how is it transported usually? Do you usually grab the carbon dioxide and then just store it directly under where you are, or people transporting it in pipelines thousands of kilometers, in tanks, on trucks, or, like, seriously, just how is it done?
Yeah, so when we've done some of our little pilot studies, yes, we have actually trucked it in, but we did a 40-ton study, so that's 2 trucks. But more commonly at the commercial scale, you would be looking at initially pipelines, and there is a huge network over the US, and they anticipate that growing as they store more and more carbon dioxide over time. So bringing up the fact that in the US, there's a whole series of pipelines over there they've been used to move CO2, naturally occurring CO2 that they've produced from the subsurface, transported in pipelines to re-inject into oil and gas fields to increase the recovery of that oil. So enhanced oil recovery has been using CO2 for 50, 60 years around the world. So we have a lot of information about how straightforward it is to transport in pipelines onshore. There are examples where offshore transport in pipelines takes place as well, and even including the repurposing of old oil and gas pipeline infrastructure to send CO2 back to depleted oil and gas fields to be permanently stored there as well. More recently, there's been increased research in shipping of that CO2 as well, and that's looking at actually going between different countries. So for a moment, the Southeast Asia perspective for Australia, if you consider that for a moment, Australia is a big LNG oil and gas, or certainly gas producer, has a lot of really good storage space. So it can send whichever energy vector might be the future of fuel going forward, but bring back that carbon dioxide that has been generated if LNG is combusted somewhere. So there's research into designing new ship models to send to Japan that might have LNG in it and bring back liquefied CO2. And so there's lots of studies going on looking at the size of the ship, what temperature you want to transport that CO2, what pressure you want to transport that CO2, and all of those things interplay about the size of that ship bringing it back. And the reason why we bring back CO2 from Japan or South Korea or Singapore is because they do not have the geology for the storage component, but they too have quite strict emissions reduction targets. So in that transition, this is one pathway to try and manage that. And researchers and industry are looking very closely at that at the moment.
Okay. So I just want to understand how big a part of the problem is that? How much complexity does it add if you need to transport in pipes or on ships? And this also relates to a question that I got from Robert on Patreon. He asked, in the context of fighting climate change, is there any need to transport CO2 or store it in large quantities? Shouldn't it be captured and re-injected into the ground immediately? The capture machinery can be built anywhere on Earth, so locate it where re-injection is easiest. And I mean, to me, that sort of makes sense for direct air capture. Why wouldn't you throw? I guess you need an energy source and you need somewhere to store it. You're saying that the reservoirs aren't that easy to come by. So how do you see it playing out, I guess? Would you avoid transport where possible, or it's not that big a deal?
So I think it sort of like hits one of the important parts that if you don't have the right geology, you can't store it in the car park of the location where you're generating it. Obviously, in terms of economics and ease, the closer you are to your point source emission or your point emission source and your storage location, that's absolutely the best option. But often is the case that they don't match up. So as I say, Japan, because it's on the margin of the Ring of Fire, doesn't have a lot of sedimentary rocks. it just doesn't have the correct geology, and so they are looking at alternatives. So there are other locations like around Australia, Malaysia, Indonesia, where the geology is much better. Now, if you can do direct air capture to sit on top of the storage location, then yeah, that's absolutely a great outcome. But you do have to look at the energy that you might want to use, and that could be run off renewable energy. And we're seeing increased interest in the ability to use waste heat to power direct air capture facilities. So if you've got your technology right, the biggest energy penalty with direct air capture is actually when you have to heat the substance that's captured that carbon dioxide to get that pure carbon dioxide off, transported, compressed and then injected. If you can use waste heat, then you've just brought that whole emissions and energy penalty right down. So if you put it in a location where there's a lot of industrial activity, that may be one way to solve some of those challenges. Otherwise, you've got to transport it to the right geology if you're using more conventional pre-combustion capture, post-combustion capture processes.
Okay, that's really good segue into the next part, which is how is it stored then? What sort of geology are you looking for? And I wanted to read out a question I think I got off YouTube here. Is it? Oh yeah, and this is I don't want to make it sound like I'm laughing at this person on YouTube. The reason I pulled it out is because it's really similar to the way that I imagined carbon dioxide storage to work. So a commenter on YouTube said, even if we get it compressed and into the ground, there will always be a stupid human who will accidentally back up a forklift onto the valve and release it all again. Like keeping a balloon underwater as he sees it. And that is definitely how I thought that it worked until I started talking to people about it, that, you've got a big cave underground, you drill a hole into it and then put put the CO2 in and then put a plug in it. I now understand that's wrong. So maybe, Linda, can you explain what kind of geology you're actually looking for?
So you're looking for porous and permeable rocks. And I think one of the hardest challenges to get across with people is the fact that you need porosity and permeability. And if you're not familiar with those terms, they can be a bit of a head bender initially. But we'll get to that. There's two main sort of like geological, and I know what that sound is. In the background.
I was just thinking I should mute myself so you couldn't hear it.
I know exactly what that sound is. How you get the tools ready. Good. So there's depleted hydrocarbon reservoirs, so they may have contained oil or gas, and they're often uneasy in the sense that you've already got a lot of information about those reservoirs because you've already drilled into them. You've got rock samples that you can measure. When you've produced the oil or gas, you have pressure data that you can actually sort of like use to make models and history match how that is going to perform over time. And you've also demonstrated that it can hold gas for a very long time. So in many respects, it can be a really easy way to get all of the right information to pick a storage site. And you can also sort of put sort of boundaries on it, because quite often it's like a geometric shape where the gas will be sitting there buoyantly under a sealing unit that stops any gas like migrating to the surface. But they tend to be a bit smaller, and they can be sort of risks associated with older fields where they haven't necessarily done a good job of the wells and the well completions and the monitoring and the management of those wells. The other main location is what is termed saline aquifers. They're basically big sandstone bodies, or they can be carbonate bodies that have water in them. And we call it formation water because it reacts and equilibrates with the rocks that are in place, and they can be quite saline. You don't want to be using locations where the water could be potable and used in the future. So you don't want to sterilize an important resource like that. But the CO2, we tend to be drilling into zones that are at least 800 meters deep. And we do that because CO2 becomes supercritical which is kind of like this crazy triple point where it's not quite gas, it's not quite liquid, not quite solid, but it's really super dense. So you can get more carbon dioxide into those pores that we're going to sort of like look at in more detail. The picture you can see there at the moment of the reservoir rock, which I assume you can all see, you can see all of those little sort of like spaces between the grains, and many rocks have different degrees of that sort of like relation of grains to rock, and it's those pores are the porosity. It's a percentage measurement of how much space there is between the grains. When we talk about permeability, it's the connectedness of those grains, and so that things can flow through. And one of the ways in which we try and sort of deal with trying to understand the fact that you don't need big pores so long as they're really well connected is to pull out the tools, Rosie, and get everyone to think about doing this at home. So you can see the chocolate bar on the picture on the left is an aero bar. You can see all of those pores, lots of big pore space. But if you actually sort of like take that and get yourself a glass of milk or beverage of choice and try to either blow bubbles into your milk or suck the milk in, it doesn't work.
Let's see
So like there's the minty aero bar that we quite often use with demonstrations. So it's really really lots high porosity, lots of space. But when you try and do that, you may find that not a whole lot happens because the bubbles are not connected. Those pores are not connected. So even though there's lots of pore space, if they're not connected, they can't move any fluids, gas, or anything else. We're going to go to an Australian icon now with the Tim Tam. And if you nibble the opposite ends off the Tim Tam and then try and blow bubbles into a glass of milk, you will see that even though it doesn't look like there's a lot of space between the grains of biscuit, there's actually huge amounts of permeability, and you will be able to either blow bubbles into your milk rather messily, or you'll be able to suck up the beverage of your choice. It's a messy pastime, but it's a great way of kind of introducing the fact that fluids can move through things that are as tiny as that, and they are nothing like a cave because we're not injecting into caves for carbon capture and storage. So
So let me just clarify a bit about this Tim Tam for the non-Australian viewers. So this is a double coat one, which is the only way to Tim Tam, in my opinion. And the idea is to do a Tim Tam slam. You bite off opposite corners, and then you use your Tim Tam like a straw. So it's just like a chocolate sandwich biscuit / cookie. But the chocolate around it means you can use it, like Linda said, like a straw. So you stick it in your milk and you can suck up milk through the Tim Tam, and it sounds a bit funny, but don't knock it till you've tried it, I guess, is the advice for that one.
Well, when you do these demonstrations, when we're talking to community groups, I really struggle to eat a Tim Tam or an aero bar for a couple of months after doing one of these demos. There's a lot of chocolate and it can get a bit like melty messy. I think my top tip is try a penguin if you're in the UK, as in the chocolate bar. So that's a really, like, it's nothing like a cave. You're not trying to, like, oil and gas does not naturally sit in caves, and that there's not a well that gets drilled into a cave and it spouts out. It's sitting in these porous media basically, and you'll be able to sort of inject that deep underground. And if we're going deeper than the point at which it becomes supercritical and below 800 meters, often 1,000, 2,000 meters in that sort of oil and gas domain again, you're unlikely to be impacting any drinking water aquifers.
So I guess that is these salt caverns that people talk about for storing hydrogen and that sort of thing, that is more like a cave that you put a pipe and a plug in. So but we're wrong to think about that for
and the volumes of those salt caverns are very, very small, and hydrogen being a teensy tiny molecule, like, you're trying to really maximize not lack of loss. But there's research going into also putting hydrogen into sedimentary formations as well at shallow depths. And I guess one of the things I didn't realize when I first sort of like started working in this area is like natural gas storage is really common and really prevalent, and it's really shallow. So people like, so the Iona gas field in Victoria and the east coast of Australia, they produce natural gas from offshore, and they store it there for that winter summer flip where you might need more gas in winter where it's cold. So all across Europe and the US, that there's natural gas storage like in many places you don't even realize, but much shallower depths. So this is a really kind of like typical way in which people actually store large amounts of gas.
Okay. Yeah, I wasn't aware of that. Let's move on to one question that is really common about when you're talking about storing CO2, which is how we can be sure that it's going to stay there forever. So another question from Patreon from Wolfgang: how long will the different storage methods keep it stored? If we use CCS as a stopgap measure, a few centuries will do, but to solve the problem, we really need storage for some hundreds of millions of years. Including preventing release from geological changes and accidental release from future generations that have lost knowledge of what we've been up to. So can we talk about how we know that it's going to stay underground, and if there's, if we know that, or if we're just hoping?
Like we know that it's very likely to stay down for, hundreds of thousands of years, because that's the time that natural gas and oil has been stored in hydrocarbon reservoirs for. And we know this because of geochemical data that we get from the oil and gas. So we know that these have been oils that have been generated from rocks that were deposited in the Jurassic period, 200 million years ago. At some point, those source rocks have been heated, generated oil and gas. They have markers from that time period that are unique to the time. And then the gas is discovered, and we can sort of like go, well, that probably got, migrated into this structure 100 million years ago, or 200,000 years ago, or whatever. So we're pretty confident on that count that the storage part is really long term. In terms of knowing where it is, there's a whole series of activities that people would get up to that will try to monitor and measure that the gas is in place and staying in place. And it's on and offshore methods to do monitoring. And, so ultimately we don't want it to come back into the atmosphere. We don't want that to happen so that we're putting more energy and more emissions into sort of recycling that through the atmosphere. So we do want it to be down there and permanently stored. So the geological assessment of the right locations is really critical. You can do surface sort of level monitoring, soil gas monitoring. You can measure like near surface groundwater and make sure that there's nothing happening there. And you can also like do monitoring of the actual reservoir itself where you've injected, or the saline aquifer where you've injected. That's an example of a whole series of different monitoring techniques that you can do for assurance monitoring, so that you can demonstrate to the community that there is no impact on the seabed or to fish and wildlife in marine settings. And the other thing that is done quite a lot is different seismic monitoring methods. So the Sleipner CO2 project, oh, there we go. They've been doing CCS like injections since like pretty much 1996, about 1 million tons per annum. So they've got, sort of like 26 million tons in an offshore area. And the way in which you use seismic monitoring is that if you've got your pores are filled with water, and then you inject carbon dioxide, you're changing the density overall of that piece of rock. And the seismic is like a kind of an ultrasound, and it starts to see the fact that there's this density contrast. And so you can actually see where that carbon dioxide is going in the underground. So people will take geological models, they will do a hypothetical injection, they know a lot about the physics and the chemistry of that water moving, and then go and shoot the seismic and see if you get a matchup. Does your predictions meet what you're actually observing? And you can tune those predictions, and the more CO2 you're injecting, the easier it is to see and make sure it's staying in place. And you can do that seismic work on or offshore.
Okay.
And then, yeah.
And so some of these monitoring methods, it's a bit small on there to see.
Yeah, sorry.
Are they, where there are existing storage reservoirs, are they required to monitor in this way? So, do we have a track record of knowing that there isn't CO2 bubbling up from these areas?
Yeah. As time's gone by, new technologies have come into play, and they've been doing demonstration activities to show that they work effectively. There's actually a whole body of work that's been done by a number of organizations over the last, 20 years, doing like controlled release experiments, like where they deliberately allow the carbon dioxide to be released underground, and then you bring all the monitoring tools together and see if you can detect it, and you can see if you can quantify that amount. And it's actually quite hard to do. You need an awful lot of carbon dioxide, especially offshore, to actually see any impact and actually observe these things. But it's done with great regularity, and
Oh, I lost Linda. I don't know if it's Linda or if it's me. Can you guys still see me moving? Might. Yeah, looks like it's on Linda's end. So I'll push on then and see. Oh yeah, she's gone from the studio, so I'm sure she'll be coming back in a minute. Okay, well I'll go back to some of the. I know you can see my full messy background now that we've got the full view. That's what happens when you have a 1-year-old in the house. I just wanted to move on to some of the the realities of CCS, because we've been working on this technology for like 30 years already. In the early days, at least in Australia, there was a lot of talk about clean coal, idea that you'd be just continuing to burn coal as per usual, and that's and then capture it and store it, and that's how we would avoid climate change. You don't hear too many people talking about the clean coal aspect of it anymore, because coal's on the way out anyway, and we now know that there's so many better ways to get rid of emissions from electricity generation. But the fact remains that we've been trying pretty damn hard to get CCS working for like 30 years, and it hasn't really done much yet. And I do have this article from Ketan Joshi, which is pretty good, that has some nice charts about how CCS is going relative to carbon dioxide emissions. So this one just shows the purple line is the actual emissions in the world versus the red line of how much has been captured. And you can see in comparison that there has been very little progress. So I'm just going to, Linda's back, so I'm going to add her. And we just lost you for a second, Linda, but don't stress.
My internet went, which is dreadfully embarrassing given who invented Wi-Fi. So yes, so I've had to go for another method. So yes, my
nearly
apologies
every
there.
single live stream I complain about how terrible the internet is in Australia. Question now, I either need to get Starlink, the Elon Musk system, or I need to stop doing live streams. I think one or the other. So you're not alone. Everybody's used to it. Yeah, so I was just introducing the next point that I want to talk about, which is the fact that, we've been trying very hard on CCS for 30 years now, and it hasn't really done a lot yet. So I was sharing, I'll put it back up again now, some charts that Ketan Joshi has made about emissions versus captured. So these are some nice charts about ExxonMobil's emissions in grey versus the amount that they have captured, or maybe it's Equinor. So it's minimal, and I think that that turns a lot of people off or makes people assume that the technology is immature. I think between what you've said today, what I covered in the previous video with Mark Allen, hopefully people are realizing that it's not really a does the technology work question. There's something else. It's I think you're missing the point if you say, oh, it doesn't work, because it obviously can, and people manage to make it work in industries where it's in their economic interest to. So I just wanted to talk now about some of the projects that, real world projects, what has and hasn't worked, and especially like what are the lessons that have been learned from, or are there any lessons being learned from the past? Because we obviously, continuing the way that we have over the past 30 years isn't going to get us anywhere in 2050. So I know that you have some specific projects in mind that you can use to talk about what you think is going to change into the future and why.
Okay. So probably one that some of you might have heard about is Chevron's Gorgon project, which is actually here in Western Australia, and it's currently the biggest one in the world. It's using the natural gas captured CO2 from the Gorgon gas field. It has about, I think, something like 16% naturally occurring CO2 present. And so they have captured that carbon dioxide and are injecting it underground, very close to where they're actually producing the gas and getting the LNG off. And so that's one case where you're not having to do huge amounts of transport. There are some pipelines. I guess the nameplate volumes that they were anticipating, something of the order of 4 million tons per annum. They're not there yet. And if you stand back and think about it, I guess from an engineering perspective, why would it open on the first day at 4 million tons? I think there's a lot of rhetoric around the fact that it is a complete failure.
I just was very cheeky and brought up my Google search for, if you look up Gorgon carbon capture, you get nothing but articles about how it doesn't work. So being a little bit cheeky to you, Linda. Sorry.
No, that's all right. That's all right. It's so far captured over 8 million tons since they got going. If you look at some of the images of the actual location and the site, it's a classic case of picking some really hard things to do. So the actual infrastructure for the capture and the wells, that's like a Google Earth like sort of like mud map we've drawn on it. That's Barrow Island. Barrow Island is a Class A nature reserve and has incredibly strict and stringent rules for what you can and cannot do there. And so Chevron has a very, very tiny footprint that they're allowed to use there. Everything that came on was like fumigated, wrapped in Glad wrap. Everything's really, really difficult to do over there to try and mitigate any introduction of feral animals because of the Class A nature reserve. So they're trying to keep an incredibly pristine location in check. So all this was done under the Barrow Island Act, which was specially sort of amended so they could do carbon capture and storage. And what they've done is like they've identified a formation where they're injecting the CO2, but rather than it being this big sort of like open sort of porous, zone that goes forever, they've actually ended up choosing a place where there's a discrete package of sand, and it's actually surrounded by muds, so it can't dissipate the pressure naturally. So what they've done is they inject the CO2, but they produce the water out of the same formation to balance the pressures. And so this is where it all went a little bit squirrely, because when they re-injected the waters, to dispose of the waters into another formation, they started having problems with their water production and their water reinjection. So that's meant that they've had to slow down the injection rate into their CO2 storage interval. So they're working through measures to try and manage their water handling, which is a really stock standard activity for the oil and gas sector. And I think they're slightly embarrassed by the fact that they were so focused on the novelty of doing the CO2 injection part, they didn't really spend the time on that more conventional aspect that they've been doing. So they're going to drill some more wells, I think, to manage the water rates so that they can get up to that 4 million tonnes per annum to deal with that. It's a classic example of a single source to single sink project where they're actually dealing with their own emissions. There's kind of like it's a zero-sum game for capturing the carbon dioxide. They have to capture it as part of doing business. So instead of venting it, they're actually trying to do something about that CO2 and learn more about the whole process as they go. And yeah, it's apparently a complete failure.
Yeah, I do think though there must have obviously been some overhyping of the project, or maybe getting a bit too excited about it. And people always like to announce the kind of long-term plans, and they do it with with wind farms as well. You always see these like 5 gigawatt projects announced, but if you talk to the developers, it's like, oh, like maybe in 2050 that's how big it will be, but for now it's going to be 500 megawatts or something. Do you think it's a bit like that, just a bit overexcited with the announcements? And so even though, I mean, you in the industry are not so surprised to hear about these quite normal sorts of problems and how long it's taken to resolve, definitely everybody else that's not an expert is like, why is it just problem after problem after problem?
I
Do you think
think if you look at any of these, like any technology or any big builds, it's easy to make an announcement. It's a whole lot harder to follow through. So I don't think CCS is any different to any other sort of activity that might be going on. If we're going to build any sort of new sort of like infrastructure for a new industry or even existing industries, they all have the problems. I think there's some other reasons behind why people might get a bit upset about it, or claim that because it's been delayed, it might be there's something else going on. I think it's a real challenge for the industry proponents to manage the level of communication that they do. And I think there's a whole conversation about social engagement with any projects in any part of the energy transition. It's a huge amount of change management for any of these projects, and there's the dialogue between the proponent and the community needs to be greater than it currently has been, I think, for any of these activities. And we've got to actually sort of like provide best information and best facts that we can about the what these different activities are.
Okay, we're running out of time, but I still want to move through to cover a few more things. And I don't know, I can go a few minutes over. I don't know if you can though, Linda. So yeah, okay. All right. Well, let's try and speed up. But we've got another example of CCS that has been working well, and then another one I think where it didn't. And then I want to talk about what's been learned from that and how the future is going to look. So we've got to try and do all that in about 10-15 minutes.
Right. Okay. Yeah. So we did cover a little bit about Sleipner before, and there's a lot of really interesting activities that have been happening in Norway, both from the capture side and the storage side. So as I said briefly, Sleipner's been injecting 1 million tonnes per annum since 1996. And the reason why Norway is at the forefront of this is the fact that they introduced a carbon tax in 1994. So if you're dealing with millions of tons per annum and you can do it cheaper than your carbon tax, then you're actually, economically ahead. So Sleipner was the first example. They have another site in northern Norway called Snøhvit, that's been beavering away. But one of the more recent projects that has been underpinned by the Norwegian government is the Northern Lights project. And they're going to be injecting captured carbon dioxide that they've picked up basically almost kind of like from a milk ground of Northern Europe harbour sites. So what they've done is they're identifying old oil and gas fields. They've identified the right sorts of ships, and they will go around Norway, go into some of the cement plants and other places, and then they'll head to places like Germany and Denmark and around, and then deposit that carbon dioxide at the head of a pipeline just north of Bergen. And that will go into a series of depleted gas fields that there'll be wells and pipelines from that shore deposit and then out. So they're looking initially at 5 million tons per annum up to 100 million tons per annum going forward. And this is where the business model part of the story comes in the economics. What these guys have done is they've actually gone out and generated a whole series of MOUs with a whole lot of different emitters around the North Sea, and that will allow for if they've got more storage demand and more that people want to actually take, then they can actually get that CO2 and the business model off the ground, because they know that they're going to exceed X million tons per annum, and that's where all the costs. It's like everyone wants to know what is the cost per ton of annum. If you've actually got oversubscription, then you can actually turn around and say it's going to cost this much. So if you've got it oversubscribed, that's the trick.
I did read that was a problem with you might know the name of the project, but there was one in the US where they built a CCS or a storage facility in anticipation of being a lot of CO2 from nearby. I think it was gas projects, and then it turned out that the whole what is it, the oil sands tar, I can't remember, you know what I mean.
I think they were doing some enhanced oil recovery. The Petronova project, I think, is maybe what you're referring to.
Maybe. And then because the industry went elsewhere, they ended up not having any CO2 to store. So, it's been really underperforming. It looks like, this doesn't work, but really they just don't have any CO2 to store. So they have to, work at lower capacity. So I guess this milk round, I like that description, is like the same as going around, from farm to farm and then putting all your milk together and going through a single bottling and distribution center, I guess.
Yep, pretty much, yeah.
Yeah, okay. And this is you've got some other slides here about other clusters. Is it the same sort of idea that you're trying to get away from single points of failure?
Yeah, so the single source to sink model that people were looking at 10 years ago, I think that in terms of like the numbers and the volumes didn't stack up well. And so there's been a move to hubs and clusters. And the example here is the Northern Territory Low Emissions Hub. And that's basically a project sitting in the Northern Territory, where Darwin is the capital city of that territory. And basically, all of the companies have come together and recognized the fact that they've got common problems, common challenges, and we're seeing that with other hubs and clusters, that if you actually bring everyone together, put them on a single location, and start to share risk and cost and infrastructure, you can start to really bring those numbers right down in terms of the cost per ton. So the project in the Northern Territory is mostly, again, in the hydrocarbon industry, trying to deal with their initial emissions, but they should be able to actually deal with a bit of a milk round from Singapore, South Korea, or Japan, and start to pull together and stage all of those activities so that you fill one like one storage site and then introduce the next storage site, so you can de-risk the fact that you have plenty of places to store, so people can invest in the capture, because the capture investment, the capital equipment for capture is fairly eye-watering to get the ball rolling.
Okay, I just wanted to finish on this chart that you have about the number of CCS projects either developed or in the pipeline, and so the bottom, like pinky red, is operational. Then the next stripe up is in construction. Dark blue is advanced development, and light blue is early development. Starting from 2010 over on the left up to 2022. And it did strike me that even some of the projects, obviously, that were in advanced development around 2010 did fail to eventuate, because you see them, the pipeline was getting smaller for a while. Yeah. But we do have some sort of steepness in that chart now. Do you feel like things are going to move now?
I think there's a sense that it has to, because CCS is a scalable mechanism for reducing emissions for the atmosphere, and the technology is there. It's now, it's getting the business case right. Is the challenge, and we can see that there's a massive upswing in the US because of the 45Q tax and the Inflation Reduction Act, which is throwing trillions of dollars trying to mitigate CO2 in the atmosphere. So this figure is actually from the Global Carbon Capture and Storage Institute. They bring out an annual status report of what's going on, and they have a website where they keep all of the projects together. So you can see them updating the amount of projects, what stage they're in, the investment, who are the partners, and so forth. They're about to release the 2023 study. So I think that picture was the 2021. And you can see that there's a lot of different projects across the world where there's more and more push towards that development and going away from just doing simple pilot or demonstration projects and really getting that commercial scale up.
Oh, is that the report already updated, Q2 2023?
No, I don't think so. It should be the annual status report. I think they launch it end of the week.
Okay. Oh, well, it's timely then for us. You can all check back on that one.
There's 2022s that you got there. So yeah, you can just see that over time. But in that little slide, I do have this big arrow at the valley of death, and I think everyone who's worked in the technology industry is very, very familiar with the fact that that is the point where things fail, and they do not rebound. But you tend to have the valley of death, and they scramble out the other side of it. Then you may actually be onto something. So I think we're expecting these numbers to go up again. Well, that's 2022, so I would fully anticipate another swing up in 2023. But it's taking it from announceables to final investment decisions, and then getting on with it is what we kind of anticipate seeing.
Yeah, I think it's it's obvious with carbon capture more than probably any other technology, but if you don't value not putting carbon dioxide into the atmosphere, how can you have a business case? As long as someone can just release it for free, it's never going to be cheaper. No matter how good the technology gets, it's never going to be cheaper to not just release it, but instead capture it, take it somewhere, store it, monitor it for for the life of the project. So it's clearly one of those projects where you can't have a business case that makes sense in the early stage of the energy transition. It's something where people need to be properly committed to, and you see it a bit with some other energy transition technologies, like even long duration energy storage, or even offshore wind in the US, especially at the moment, is having a huge crisis because it's one thing for people to make net zero plans and to talk about them, but it's another thing to actually give companies enough certainty that that you really mean it, that there's really going to be money for doing these expensive things. And I think across the board we are struggling a bit between what people say that is their net zero target and what industry believes it's strong enough to invest billions of dollars in it. So I don't think that,
and I think some of that upswing is partly, you probably track against some of the COP26 announcements and subsequent announcements, is also the signals there for industry that this is coming, and they're starting to sort of get on the front foot, irrespective of whether they can, whether there is a a carbon credit or other mechanism that's going forward. So as those come into play and the different carrots and sticks that the governments are starting to pull together, that should actually happen. In terms of the finances, that dip is also kind of concurrent with a really low oil price as well. So in terms of people talking about oil and gas having these massive coffers to just do it, they're only one part of the equation. And if they were busy trying to sort of survive through a massive downswing, and there's no value to carbon dioxide, makes it really hard for them to sort of shoot off and invest in that. They're starting to see that economic argument is starting to swing and change. So there's some really there's some fundamental changes that are going on that will, in theory, see these numbers shoot up. But not every project that's announced will get to the end of the line for any sort of sector. So I think there will be projects that will make it and projects that won't, for a whole range of reasons. And we've just got to try and sort of see how to ride these things out.
Yeah, I think that's it's going to be really interesting to see how it goes. And I do note that the cost of CCS is now getting quite close to the price of a of a ton of CO2 in the either compliance or voluntary markets. So I mean, we'll know soon if it can work, because once those kind of two curves cross over, and it should make the CCS projects profitable. And if it doesn't take off when that happens, then I think that that might be the end of it. But let's see, right at the start you had some projections about CCS in future scenarios, and I think without having CCS in our toolkit, then it is going to be harder to the point of being maybe impossible to actually get to net zero, because I mean there's some technologies hard to fully abate, like steel, but at least it's possible. And then actually there was a comment about cement from Frederick. Clean coal may be a fiction, but clean cement may still be needed in the near term. It is really hard to get clean cement if you don't involve CCS. And then there's some that are even, not just really, really hard, but actually impossible to see how that you would actually get to zero emissions from agriculture, for example, without a bit of direct air capture or something. BECCS even. I know that's another controversial one. Yeah. Anyway, we better wrap up, and I have purposely avoided any questions about, should we, and I don't know about, is it all a scam from oil and gas or enhanced oil recovery, all those controversial things. I do want to address them in a video coming up, but today I really wanted it to be about, how does this work, so that people can actually understand it before making up their mind about whether they think that we should be doing it, and whether it's all a big scam. So definitely want to thank you, Linda, for bringing some facts into some facts and some education into this. I learned a lot. It is wild to me. It's probably, out of all of the topics that I've covered on my YouTube channel, CCS is the one where my just general understanding from just reading articles and watching YouTube videos, this is the one topic where my general understanding was so far away from the reality. Like, there's no other technology that I had such a wrong idea about how it works from what is out there. And so, I'm really glad to have been able to understand a bit better. And thank you for taking the time, Linda.
Oh, no worries. Glad to help.
So I just need to wrap up by thanking the Patreon team who support the channel. And I've read out a few questions from people today, and that's something that we always do with the Patreon team, or at least I try really hard to remember to do it, to share what topics are coming up and to ask for input. So if you want your specific questions answered in future videos or live streams, then that's a way to get that done. Also, the other people this couldn't happen without is the sponsor, WeatherGuard. And we also do a podcast on the WeatherGuard Uptime Wind Energy podcast, which I co-host every week with Alan Hall and Joel Saxon. Links to that in the description, along with the tech newsletter. We talk about all kinds of clean energy tech news. And recently we've been talking a lot about the ongoing wind industry crisis. There's so much going on. It's a bit of a traumatic time for offshore wind, similar to probably what it's felt like being involved with CCS over the past decades. And then next video coming up is going to be on community power. So that's a nice, warm, fuzzy feeling topic to look forward to coming up probably next week. Yes, thanks everyone who tuned in to watch. We'll see you in the next video. Bye.